on X-ray photoelectron spectroscopy. Today we have Dr. Biesinger, who's the Director of Surface Science Western at Western University in Ontario. So Western is a leading surface analysis and materials characterization facility, and Dr. Biesinger is an internationally recognized expert in XPS. He has several highly cited publications in the field, which focus on the improvements in both sample analysis and data interpretation techniques, particularly in the analysis of transition metals. So we thought that it would be very interesting for our pool of students who are users of XPS for biomedical, the characterization of biomedical surfaces, essentially. So Mark Biesinger authors and maintains the X-ray photoelectron spectroscopy reference page, which is a repository of techniques, tips, and reference materials designed to help XPS users worldwide. So we invite our students to have a look to this, his webpage and all the information that is contained in there. So Dr. Biesinger is also the author and co-author of over 65 peer-reviewed publications, and he has issued over 3,000 proprietary technical reports to industry. He was awarded recently the Fellow of the International Association of Advanced Materials, and he was a Vibleo Scientist Awardee in 2021. And he finally serves as the Secretary-Treasurer for the Division of Surface Science at the Chemical Institute of Canada. So, Dr. Biesinger, the floor is yours for the presentation on XPS. Thank you.
Thank you very much. A little bit about Western. You may know us from our football rivalry with Laval. We are Canada's 7th largest university, established in 1878. And we've got about 40,000 undergraduate and graduate students. We have a very good business school here, as well as a highly respected medical school. And we're also, our science and engineering faculties are also leaders in materials and surface analysis within Canada.
Western is a bit like the mirror of Laval University in Ontario. With
yep.
Like almost the same size of number of students, about the same, Faculty of Medicine, Faculty of Engineering. So yep. Certain differences, but globally, we hover. Sometimes University of Laval is at the 6th position and Western is at the 7th with respect to research money. And the year after, it's just below. So we are like this.
Kind of the same. You're right. Absolutely. I agree. So we're down in London, Ontario, which is nice, conveniently located between Detroit and Toronto. A little about Surface Science Western. We like to think we're Canada's leading surface analysis and materials characterization laboratory. We have 15 full-time staff members with expertise in everything from chemistry, geology, physics, metallurgy, materials science. We're run a little differently. We're run as an ancillary business unit for Western. So we pay rent, we pay everyone's salaries, we pay for all the maintenance of the equipment, for upgrades, and even purchasing some new equipment. So we're run like a business for Western. And our user base includes not just Western graduate students and faculty. We work with university groups around the world, but our big business is we work with between 150 and 200 different companies from across North America annually in a variety of different sectors. We have a strong presence in the automotive world. We also do a lot of work in aerospace defense, mineralogy, mining companies, helping them improve their recovery of their various ores and those sorts of things, as well as a variety of other areas. As you can see, we have a very long list of instrumentation. I won't go through them all. We were very fortunate about 2 years ago, we had a large CFI grant, and we placed about, it was somewhere around $11 million worth of new equipment into the facility, including a new state-of-the-art XPS, high-resolution SEMs, a couple of variable pressure SEMs, a micro-CT, a new field emission Auger, as well as a number of other pieces of equipment that you'll see here. I won't go through the entire list, but quite extensive. We have a long-standing expertise in secondary ion mass spectrometry. In fact, we have 2 dynamic SIMs, a time-of-flight SIMs, and then one of our neighbors in the research park where we're located They also have a dynamic SIMS and a time of flight SIMS where they're doing mineralogy work for companies in the world. So we have a kind of a cluster of SIMS instruments within, 100 meters of each other. So XPS, I'm going to go through some of the basics, a little bit about curve fitting, and then some of the more advanced work that we've done. Some of the background for some of this work. Over the years, myself and others have noted issues within the literature with interpretation of XPS spectra, in particular the interpretation of transition metal XPS. And there has been some proliferation of faulty data out there with ongoing citation of erroneously interpreted data. And we're even seeing this in some very highly cited and well-regarded journals. The point is that XPS is not just a point and shoot type of technique. There does need to be expertise in not only the analysis side of things, but also on the interpretation side of the data. And myself and others in the XPS community have been working very, very diligently over the last couple of years, particularly to try to remedy some of this. And these are some of the papers that have come out. There's just another journals or there's a book coming out and things like that. So people are working to try to improve the quality of the data that's out there. The instrument in the front there is the Kratos Axis Ultra, and I understand that you guys also have an Ultra at Laval. So this was an instrument we got in around 1999, 2000. The instrument in the back is the Kratos Axis Nova. That instrument in particular is set up as more of an industrial instrument where you put in a whole bunch of samples. It has a large platter that you can put a lot of samples on, set it up for automated analysis. In about 2.5 years ago, I guess it is now, we replaced the Ultra with the latest Kratos Axis Supra, state-of-the-art instrument. It comes with an aluminum K-alpha source. It has a stage that you can heat up to 800 degrees Celsius. You can cool it down to liquid nitrogen temperatures. It has a fracture chamber where you can fracture samples in situ. On the front of it, over here, you can attach a glove box to, so you can introduce samples into the instrument without exposing them to air or water. And it also has the latest gas cluster ion source, which allows you to do depth profiling and sputtering and cleaning of materials without really damaging them or changing the oxide properties of them, as opposed to the older argon ion sources, which were a monatomic ion source, which you always had to worry whether you were using that. The ion beam would reduce materials that you were looking at and change the chemistry of those materials. Everything's fully automated. It's been pretty handy during the pandemic. I can go in, load samples up on Monday morning, and then run for a couple of days from my office here in the lab or in my house. So it's kind of handy that way. You can do everything by remote control. So XPS is based on the photoelectric effect, which is what Einstein actually won his Nobel Prize for back in 1921. It was further turned into an analytical tool by Kai Sigbon, who also received the Nobel Prize in 1981. Now, the way it works is you take X-rays to probe the surface. Photoelectrons are produced. Those can escape from the surface, so the outer few nanometers of the surface without loss. You measure the kinetic energy of those, and that tells you, using the Einstein equation here, the binding energy is the energy of the X-rays minus the kinetic energy that you read, and that you can tell you what you have. So start with an X-ray. In our case, it's aluminum K-alpha is the most common X-ray used in XPS right now at 1486.7 EV. Knock out a photoelectron from the core, measure that kinetic energy, use this equation to tell you what the binding energy of those electrons were. Some spectroscopic nomenclature. If I talk about the carbon 1s or the nickel 2p3 halves, it's the principal quantum number, orbital angular momentum, and then the total angular momentum is what they use for this kind of nomenclature. Some X-rays that have been used for XPS are, some of them are shown here. The most common ones are the aluminum source, followed by the magnesium source. We also have a zirconium source. Is that right? Zirconium, yes, zirconium source on ours. No, silver source, I'm sorry. Our old instrument had a zirconium or a zinc source, a zirconium source it had. We have a silver source on ours as well as we have a UPS source, so helium-1, helium-2. And the energy of the X-rays tells you, what core levels you can excite. So you can't excite core levels that have binding energies greater than the X-rays that you have, energies that you have. So the aluminum is the standard. Magnesium gives a higher X-ray flux, and you can also use it to help remove Auger line interferences. I talked about the zirconium and silver sources, which are more higher energies, so they're accessing deeper core lines, as well as you can have electrons escape from a deeper surface. So you can get instead of analyzing a few nanometers, you may be down to 10 or 12 or 20 nanometers more when you have the higher X-ray source. Helium-1, helium-2 are used for ultraviolet photoelectron spectroscopy. And then you can go to a synchrotron and use their X-ray source to have a tunable source that allows you to optimize your surface sensitivity of the samples that you're looking at. So when I talk about depth, the main thing that you may hear from people is they talk about inelastic mean free paths. So the inelastic mean free path is the depth of the photoelectrons that it can escape from the surface without loss. And so normally when we talk about how deep we're analyzing, we're looking at 3 sigma or 3 inelastic mean free paths of depths. If you want to change your depth of analysis, you can change your X-ray source, which we talked about, or you can change the angle of your sample. So if you have a 90-degree takeoff angle, which is what you have over here, where the electrons are going straight up to here, and your spectrometer will be up in this area, that's the maximum depth that you can get. So there's no loss. But if you angle your sample, you now change the amount of material that your electrons have to go through. And so you're making it effectively a shallower depth that you're reading from. So at a 30-degree takeoff angle, you're at about 50% of the depth that you would normally get at 90 degrees. And at a 15-degree takeoff angle, you're at about 25% of the depth of what you would normally be at 90 degrees. So XPS, so an example of a survey scan where you can go in, you scan from, say, something like 1100 or 1200 EV down to 0 EV binding energy, and you get all these peaks in here. And the various peaks that you have tell you, well, what elements that you have. And also you can then measure the area under the certain peaks, combine that with a relative sensitivity factor, and quantify what you have. So you can tell, okay, I have so much carbon, I have so much fluorine, oxygen, etc. So that's a very handy thing to do. If you're looking at a variety of samples, you want to know what's on the surface. XPS can tell you quantitatively or semi-quantitatively what you have at your surface and how things are changing. So very useful information. If you're going to go through and try to identify unknown peaks, well, how do you do that? Well, there's functions in the software that allow you to look through libraries and see what kind of peaks you have. There's books like this, which is the, so this is the old, boy, this one's pretty ripped up. This is the Phi reference book. So you can see we have spectra in there with tables telling you what you have, what common chemical states that there are. We have line position tables on the back. where you can go and say, okay, well, I have a peak at 400. Well, what could it possibly be? And you look through the table, oh, it could be nitrogen. So you have things like that. Tables like this, where you list all the different binding energies. It's nice to know, it's nice to have something like this book that has reference spectra, because one of the big things that gets confusing is, well, we have all these peaks listed, but we need to know if I have only a small amount of, say, iron, well, what's the strongest peak? What peak should I be looking for? And so then you can look in a book like this, and if I can find iron, you can look at the spectrum and see, okay, that's the strongest peak. The 2p peaks are the strongest ones. So if I think I have iron, those peaks should be there. And then if I want to confirm that, then, well, maybe some of these smaller peaks might be here. Maybe this 3p peak or this 3s peak might be there if it's a really strong signal. So some of those things can get complicated, where you need to understand what peaks should be there. And, you know, if your strongest peaks aren't there for your element, and you're seeing a peak that might be for that element, it shouldn't be that element unless the strongest peaks are there. I hope that makes sense. If we look at chemical state determination, so if you have small shifts in the core level binding energy, those are indicative of chemical state changes. So you can tell, you know, do you have the metal versus the oxide, silica versus silicone, fluoride versus fluorocarbon. As you withdraw valence electron charge, you decrease the shielding and therefore increase the binding energy of those core electrons. If you add valence electron charge, you increase shielding, decrease the binding energy of those core electrons. So that's the very simple. And for a lot of things, that's all you need to know for many species. For elements that have uncomplicated peak shapes, a simple binding energy reference is usually sufficient. So something like fluorine, which only has one nice sharp peak, or carbon. There's nice databases out there. The NIST database would be a very good starting point for anyone who's doing work. It's searchable. You can find out, you know, it's gone through the literature for you, and it's done a pretty good job. The Phi handbook, which I just showed you, is another one that has a good listing of binding energies. For the most part, literature values range from good, so those databases are quite good. There is some incompletion out there. There's lots of samples and materials that haven't been analyzed yet, and we don't have a good reference on. And then there's some wrong values out there as well, and I talked about proliferation of faulty data. So how do you believe the literature? A couple of things you can do. You can check the literature for, you know, things like whether the instruments, have they reported that the instrument's been calibrated? You know, if the instrument's off, it's reporting the wrong values, and that can screw up interpretation. Things like charge referencing. So when you shine X-rays at an insulator, it kicks off photoelectrons. Well, those photoelectrons, if it's insulating, you build up a charge on that surface, a positive charge on that surface. And so then as the next electrons leave, they're going to start slowing down because the opposites attract. And so you change the kinetic energy of those electrons that are coming off. So that's called sample charging. And you fix that by shining either an electron flood gun on the surface, or sometimes they use an argon flood, or a combination of the two. And you get a steady state. You overcharge the other drag, but you get a nice steady state so that your peaks hold at the same position, but everything's be shifted down. And so you have to charge correct. So what are you charge correcting to? Are you charge correcting to adventitious carbon, which is a common method where you shift everything to the main peak of carbon set to either 285 or 284.8 EV? Well, which one did they use? Do you shift it towards a known internal component of your sample? So you know you have in your sample, you know you have titanium dioxide. And so you shift it to a common titanium 2p 3/2 peak. So you have to report all that, and the literature should report all that. They should report you know, all the conditions that things were taken at and what they've done to the material and the sample and the data processing. So we're back to our survey spectrum. If we zoom in on a specific area, so we're going to zoom into the carbon 1s spectrum, we can take what's called a high resolution spectrum. And so these are higher resolution settings, and you can see that that peak is actually can be deconvoluted into a whole bunch of different peaks. And each of those peaks have different binding energies, and then you can figure out, okay, well, what do all these peaks mean? So this peak, we have so much carbon bound to carbon, carbon bound to hydrogen. Up here, we have some CF3 functionality, CF2 functionality, oxide functionality, etc. You can break all that kind of stuff down and quantify. So the area under the peak kind of tells you how much of each of these species we have. So for high resolution spectra, so that's a 1s peak. Generally, like I said, it's just a binding energy shift gives you most of the information. For things with P, D, and F orbital spectras, you can get a lot more complicated for various reasons. So I'm just going to stop here, and I'm going to share my screen. Let's see here. Stop. And I'm going to show you just very quickly how I go about processing some spectra. And so this is called this software is called CasaXPS. So you mentioned that you guys use the Phi multi-pack system. Probably very similar. It's just a different way of doing things. But I'll go through and do some quantification of a survey scan. So this is a survey scan. This was just a multi-element sample. So we've got all these peaks here. If we can go in, we have a library. So if I know a little bit about my sample, I can go to the periodic table. So, well, I know I've got carbon on the surface because it was air exposed. So I know there's going to be carbon. I know there's going to be oxygen. So I can click on oxygen. There's peaks for oxygen here and here. And then it's like, well, I don't know much else about my sample. I know it was a silicate. So I can click on silicon. Yep, we've got our 2 peaks for silicon, but what are all these other peaks? So then I can go over here to a library. And if I zoom in on a peak, I can click on it. I see, well, it's at a binding energy of around 1068, somewhere around there. Well, what would that possibly be? Oh, it's a nice single peak. So it's a 1s, likely sodium. So let's go back to our scan and say, okay, we've got a sodium peak here. Yep. We have another sodium peak here. So yeah, that's present. We've got some sodium peaks down here. So they're present as well. And if I really want to, you know, if it's an element that's new to me, I can go into my Phi handbook and look up sodium just to make sure I'm getting everything and compare the spectrum that I have for sodium with what I have here. And say, yep, the ratios look right. The 1s should be my strongest peak. The 2s and the 2p peaks are much weaker. And we have this strong Auger signal that has a whole bunch of peaks. So it's not just this peak right here, but it's also this peak right here and a bit of this structure here as well. So I can see that from that kind of handy book, having that kind of reference there. If I go in and say, okay, I've got some other peaks here. Let's find out what these are. So if I click on that one there, and it's got, you can see how it's a doublet, right? So we've got 2 peaks close together. They look like they're about 2 to 1 ratio. So that kind of says to me, well, that's a p orbital because they generally have a 2 to 1 ratio. So if I look through my list, I got, well, it could be some of these, but I know that it's calcium. And you can see we also have this calcium 2s peak up here. We have a peak here. We can click on that. Nitrogen. And it looks like we've got most of the stuff. There may be a little something here. 180, well, that's a tough one. Maybe bromine. Looks like bromine, we got a bit of the 3D structure here. May not be. So once I've done that, I can then label the peaks that I have on my surface. And so we've got carbon, some oxygen peaks, some silicon peaks. Don't want that one. That one. And if we apply, so we then labeled peaks. And then from those labeled peaks, we can, what we want to do, we want to measure the area under those peaks so that we can then apply the relative sensitivity factors to quantify what we have. This particular software has a neat little function where I just go create from labels. And so whatever I labeled, it gives me a background area, but I don't want all of them. So I'm going to get rid of things like the duplicates. So I don't want the oxygen Auger. I want to quantify with the strongest peak. So I don't want the oxygen 2s. I want to just use the oxygen 1s. Same for silicon. I'll just use the 2p. For sodium, I'm going to use the 1s, which is the strongest one. So I'm going to get rid of the other peaks for them. And same for calcium, the 2p, etc. And so now I have most of those peaks. And I can even go in and look at them. Okay, my backgrounds look about right for that one. If I scan over, we might do a little adjustment there to get so that I'm just right down to the background. Same with the sodium or the nitrogen. The calcium wasn't where it needed to be, so I can move that over. Move the silicon, move the bromine a little bit. And if I go apply, I've now quantified a spectrum. And so instructions like that, I have that kind of stuff on my website where you can follow along and use the software to analyze it. The one thing you do have to make sure that you're using is the correct relative sensitivity factors. So different instruments have different relative sensitivity factors. Some are based on Schofield tables, some are based on empirically derived sensitivity factors based on the instrument that you're using. So these particular relative sensitivity factors are from the Kratos systems. So they're set up to take into account some of the things that go on in a Kratos system. So they're a little more accurate that way. Okay, so that's that one. And then I was going to show you how to curve fit something. So I'm just going to do a simple curve fit of a carbon 1s spectrum. And this was just, let's see which one, sure, that one will be fine. This was from an adhesive disc that I use sometimes for mounting samples. And so it's good to have an idea. So if we go into our quantification, we're going to put a background. And I tend to use the Shirley background for most. I don't know if you're not familiar with that. There's a couple of different backgrounds you can use. You can use a straight line or a linear background. You can use a Shirley background, which takes into account loss of electrons as we move up the binding energy scale. And it works quite well. And then there's another background called the two-guard background, which has been shown to be a little more quantitatively accurate, but it's also a little more hard to apply in complex systems because you generally need to have your elements well separated. So the Shirley background is a nice compromise, and it generally does a good job for what most people need. There's not too often that I need to use the other type of backgrounds, but some people swear by the two-guard background and use it a lot more. I've found that for most systems, error that you get from a Shirley background is marginal compared to errors that are introduced other ways within the XPS analysis. So if we look at the carbon peaks, so then we can just add some peaks. So there's a peak, there's a peak, there's a peak. And you can kind of see that there should be peaks there. That kind of makes sense. And if we just hit fit like that, we're already, quite a long ways away to having an accurate fit. This looks a little off. Sometimes what I like to do, if it's not a well-resolved peak, so for example, if this was more of kind of a flat line, but you knew that there was a variety of species mixed in there, you have to start constraining your peaks. And so, for example, this peak we might constrain to have the same full width half max as the main peak here. And you can see that now that's fitting a lot nicer up in this area of this. Whereas this one here is well resolved. We know that that's the natural line width that we have there, but it's not always the case. And so you can play lots of games with curve fitting. If you look at the binding energies, you can see that this is shifted down. This is at 280.62 EV, which doesn't make sense because that's too low. So this is a non-conductive sample. So we have to charge correct that sample. So we would go in, do processing to calibration. And depending whether or not I was doing organic materials or transition metals or something like that, I would either choose to have this peak moved from 280.62 to either 285 or 284.8 EV. And we just click on that. And actually what we'd want to do is charge correct all these here because they're all from the same sample. And if we hit apply, we've now shifted this peak up to 284.8. So now we've charge corrected this sample or these series of spectra. But we've also charge corrected the oxygen 1s spectrum, and we've also charge corrected the silicon 2p spectrum as well. So those are some of the things, and you can get much more complicated where you start constraining peak widths. You can constrain the positions of peaks, and it will depend on how well resolved your spectra are. Sometimes you'll get spectra where you can see here we've got stuff in here, but if we just let the math fit this, it might not fit this correctly. You want to fit peaks with chemistry in mind as well, and that you have to understand what your sample is and make some decisions on how you're going to constrain these things. All right, any questions on that so far? Or should we wait till the end? We'll wait till the end maybe for questions. Is that okay?
As you wish, that's fine. We can perhaps take a couple of minutes for questions if the audience have.
Sure.
Okay, I have a question here.
Mm-hmm.
How do you know? Thank you for the presentation. It was very nice.
Yeah, not done yet.
Yeah, I know.
2 minutes.
How do you know how many peaks you have there?
So that gets back to it helps if you understand the chemistry of your system. So if I look at this peak, this silicon peak, from experience, I know a couple of things. First of all, the silicon 2p is a doublet. So I've got to put a doublet in. So if I add a background and a doublet of peaks in and fit it, it kind of looks right, but that may not be the correct doublet. So I have to understand from reference spectra and references, well, what does this doublet look like to tell me whether or not, do I have one species here or do I have multiple species here? So the first peak is a 2p 3/2 peak. The second peak is the 2p 1/2 peak. They're going to have, based on quantum mechanics, and I'll talk about this in a bit, they should have a peak area ratio of 2 to 1. So this should be twice the size of this peak. So if we constrain that to be half the size of that, and we refit, now it's getting a little closer. But, where should this peak be in relation to this peak? Well, again, we look at our reference book, and it tells me that silicon should be, the spin orbit splitting should be 0.6 EV apart. So this peak should be 0.6 EV above that peak. So A plus 0.6. And you can see that. So if we look at that now, no, that's not right. We got some extra chemistry there. We should also have that this peak should be probably the similar full width half max to the main peak. So if we make that constrained, so now we have two peaks, a doublet. with the right proper splitting, the right ratio of area, and the right full width half maxes. So now we see, okay, this doesn't fit very nicely now that we've got it all constrained up. So there's probably more chemistry there. So if we do a copy of those two peaks and paste, and we'll hit fit again, oh, now we're looking like we've got something, right? So we've got one species and another species. So then we look at the binding energies. So where's our binding energies? So the first peak is at 101.7. The second peak is at 103.1. Well, the second peak is probably silica. So that would be 101.2, 101.3. That's a silica. This one down here, well, this is an organic system on a copper, an adhesive. It probably had some release paper on it. Release paper is made of silicone. I bet that this, the thing at 107.8 is a peak for silicone. So those are kind of the processes you go through to curve fit these things. Does that answer your question? Or does that get you further along?
So now between the first peak fitting that you had and this one, which one you think is like the correct one?
I think this one's the correct one now compared to what, and you can see that the fit of the peak, the envelope is almost perfect now, right?
Yeah.
And we've been able to explain the chemistry. The full width half maxes make sense. The peaks, the doublets are fit into there. So we haven't, sometimes you see papers out there and they've just thrown a whole bunch of peaks in there of various peak widths. One peak will be really skinny, one peak will be really wide with no real reason why, other than the math thought it was a great way to do that. Well, all the math does in the software is try to get the best fitting of this whole envelope. But that best fitting may not make chemical sense. So we have to make sure that what we're doing makes chemical sense as well, right?
Right. Yeah. Thank you.
Okay. Any other questions?
Professor, I have one question. How can I know that the peak, the area that I found for a certain peak is exactly, for example, if it's, I don't know if it's too large or too tiny, how can I know that?
It can be tough. I mean, if the resolution is there, so for example, the resolution is here, that we know that this is the right peak width for this one, because we've got lots of peak there. We know that it must have a full width half max of, around 1.2. This one here, we have the resolution, we can see the 0.8. But here, say for something like this, it gets a little harder, you can see, well, we probably got a peak in here. This one here might be broader or narrower. So you have to you can set limits on it. If you look at standard materials, you can tell from them that, okay, if I have a metal oxide, generally the full width half maxes for them will be between 0.8 and 1.2 EV in the option 1S. If I have a hydroxide, it's generally a little thicker. It's like 1.5, 1.6. If I have something like sulfate, 1.8, 2. It's a lot of it's based on seeing lots of samples and having some of those libraries. And that's why I've put out libraries in my website that kind of also list things like full width half max, what the spin orbit doublet splittings are, as well as binding energies, where, the range of binding energies for materials.
Okay, thank you.
Okay.
We will move on and we'll take the questions at the end of the presentation.
Sure. Okay, so we've done that. So now if we get into the transition metal species, we get a lot of more complications. So it gets complicated very fast. So we have things, we talked about spin orbit splitting. So we're going to have those kind of contributions. If you look at metallic and conductive species, a lot of times they can have an asymmetric peak shape. You can have things like Plasmon loss structure, shake-up structure, And then the big one in the transition metals is multiplet splitting. And then for a lot of these species, you're going to have overlapping binding energies and peak shapes. So if we look at spin orbit splitting, and we talked a little bit about this, the S levels give rise to a nice single peak. So it's very simple. So they're like things like carbon 1s, oxygen 1s. If you get into things where you're looking at the P levels, D levels, and F levels, you get the spin orbit splitting. So you get 2 peaks instead of 1 peak. And they're going to have specific area ratios based on the number of electrons within those orbitals. So for your P orbitals, the 3/2 to 1/2 peaks, you'll have 2 to 1 ratio of electrons. For the Ds, it'll be a 3 to 2 ratio. And for the Fs, it's going to be a 4 to 3 ratio. And that's just basically based on the number of electrons in the different orbitals. And so if you have a peak, it should have a 2 to 1 ratio for a P orbital. If it doesn't have a 2 to 1 ratio, you may have multiple species there. You may have some overlap from another element mixed in there. So you're going to have to look at those sorts of things. For a metallic species, you get interaction of the core electrons with the conduction band, and this will cause small losses in the kinetic energy. And this shows up as this asymmetric tail, which you see here on this titanium metal spectrum on the higher binding energy side of the peak. And this happens for something like graphite, also shows this. Carbon nanotubes, things that are conductive, will show this asymmetric peak shape. And so you have to model that when you're trying to quantify various systems. Plasmon loss structure, not as much of an issue in high resolution work, but in survey spectra, I've seen in the literature where people have seen these plasmon loss lines, say from something like the aluminum or silicon or other species, and they've actually tried to say, well, this is a peak for silicon or magnesium or some other element, when really all they have is this loss structure, these plasmon loss structures for aluminum or silicon. And so it's just mislabeling I've seen out in the literature. Shake-up structure, you can have a probability that an ion will be left in an excited state. And so when this happens, the kinetic energy of the emitted photoelectron can be reduced. And you'll see this as a higher binding energy peak above the main line of the peaks of the spectrum. And a classic example of this is the copper 2p spectrum of copper 2 species, where it's almost diagnostic that you see in copper 2 species, you see this shake-up structure above the main 2p line. And finally, multiplet splitting. This arises when you have an ion with unpaired electrons. So for example, if you have chromium 3 species, that's a 3p6 3d3 system. So you have unpaired d electrons. You have 3 unpaired d electrons. And so then when you create a core electron vacancy by photoionization, you can get coupling between the unpaired electrons in the core with the unpaired electrons in the outer shell. And when this happens, you get a number of final states that are produced that are now seen in the photoelectron spectrum. And so instead of a nice single peak, so this is the 2p 3/2 peak, there would be a corresponding 2p 1/2 peak over here somewhere. But for chromium 3, which you would think, okay, it should be just one nice peak at a single binding energy, you get this multiplet split peak shape that is no longer a nice single specific binding energy. And so this was modeled back in the 70s by Gupta and Sen, and they went through the various transition metals. You can see some of the modeling for the different peak shapes that they suspected would be seen for different transition metals. And if we look at across the transition metals species, the samples in green don't have any unpaired electrons, so they're either they don't show any multiplet splitting. The ones in red show significant multiplet splitting. And then the ones in yellow, they do have multiplet splitting, but it's either not well resolved or it shows up kind of as peak broadening only. And so with all these types of complications, so how do we accurately identify the species that are present? And then further, how do we quantify the species that are present? And so that's kind of an important step, you know, how much do you have of each thing? And so our solution has been to develop standardized fitting procedures for the different metal 2-piece spectra. We went through the literature, looked through everything that was out there, and then we did an extensive analysis of quality standard samples. And we made sure we would check the standards to have that they were the right thing. We went through some systems where we had to figure out, make sure that the surface we were looking at was the same as the bulk, etc. And then from that, we developed these fitting procedures that take into account things like spin-over splitting, peak asymmetries, lost structure, shake-up structure, and multiple splitting. And then we'll use the total photoelectron yield for each of these species to determine the percentages present in unknown samples. And so what do I mean by that? If we look at something that doesn't have multiple splitting, so say the scandium 2p spectrum, so we need to take into account that we have doublets. And again, they're going to have a 2-to-1 peak area ratio. They're going to have the 3/2 peak is going to be a certain distance from the 1/2 peak. So we constrain that. We're also going to take into account that something like, say, the scandium metal is going to have an asymmetric peak shape. So we'll use curve fitting parameters that'll give us an asymmetric peak shape in our unknown sample that then quantify for that. Because if we didn't have an asymmetric peak shape, then this peak would be there would be more intensity there. So you're changing the amounts that are present. And so you can take these fitting parameters and figure out, okay, so I have so much scandium oxyhydroxide, so much scandium 3 oxide, some suboxide, and so much metal on this surface. Relatively straightforward. Similarly for titanium, you can do the same sort of thing. Look at a bunch of standards materials, find out the binding energies that you would expect for those materials, do the curve fitting that includes an asymmetric peak shape for the metal, constraining the full width half maxes of the different peaks, constraining the peak separation as well as constraining the 2-to-1 ratio peak areas for those to be able to then consistently quantify the same way different titanium systems. So then when we get into species with significant multiplet splitting, we got into this back in early 2000s, 2003, 2004. We were looking at chromium materials, so chromium on steel. When we got looking into the literature, we realized that the literature was not very good. So there was even databases that were quoting single peak binding energies for compounds that are known to have multiple split peaks, like I showed you for the chromium 3 or the chromium 3 species. What they were doing, they were actually taking that structure, some of the literature, and they were, instead of realizing that it was just chromium 3, they were assigning those different multiplet split structures to different chemistries. So they were saying, okay, we had chromium 2, chromium 3, chromium 4, chromium 6 claim, when really only chromium 3 was actually present. And so what do I mean by that? So they were saying that, that peak was chromium 2, that peak was chromium 3, chromium 4. I even saw some were saying it was chromium 5, which I'd never heard of, chromium 6 down here. When really all they had was chromium 3. And so they were misinterpreting the structure of this, the multiple splitting of this. And so what we've done, we've taken a series of samples here, standard samples, very clean standard samples, taken the spectrum, and then we looked at these and say, okay, well, I need to be able to make a peak fitting routine that I can apply over and over again that allows me to quantify how much chromium oxide I have, how much chromium hydroxide I have, how much chromium 6 I have, how much chromium metal I have. And so for something like chromium 6, we only have a nice sharp peak shape because there's no multiple splitting, there's no unpaired electrons. So we have a peak at around 579.5 eV. For something like chromium 3 hydroxide, we can use one broad peak set at, I think it's 577.5 eV. And then for the chromium 3 oxide, where we have this multiple splitting, we'll use a series of peaks that mimic the peak shape of the chromium 3 oxide. And we'll constrain their areas, their positioning, to make, really what we're doing is we're making a standard spectrum that we can then fit into our fitting routine. And so that's all that this is. And then when we're done with that, we can go in and say, okay, in some unknown samples, so this was a decorative chrome plating. Before the surface treatment, we have so much chrome metal and mostly chrome hydroxide on the surface, chrome 3 hydroxide on the surface. But after surface treatment, you can see that this bump here kind of shows up. And we have so much chrome metal, but now we have some nice clean chrome oxide in amongst our chrome hydroxide. And we can do it again. This was a chromated zinc plated steel. We have so much chrome oxide, so much chrome hydroxide, 3 hydroxide, but then also we've got chrome 6 showing up on this surface. So we've taken these parameters and applied them over and over and over and over and over again on a variety of different systems, and they work, giving us being able to quantify or semi-quantify the amount of different species within a system. And chrome's works really well. There's not a ton of different chrome species, so it works. If you start getting into something like nickel, so if you look at the nickel metal, we have an asymmetric peak shape with some satellite structure, which we have to take into account. But if you look at something like the nickel 2 species, so we have nickel 2 oxide, nickel 2 hydroxide. And again, we were seeing in the literature where people were saying, okay, well, this is the nickel 2, this is nickel 3, and this is satellite structure. We'll just ignore that completely. And then they'd look at the hydroxide and say, well, this is just nickel 2, and maybe there's some nickel 3 down here. And they were trying to fit chemistry in where really they only had nickel 2 oxide or nickel 2 hydroxide. And so again, we've taken a series of peaks that are fully constrained to mimic the shape of this structure and position of this, the structures we're seeing here in this spectrum. And again, if you look at something like nickel ferrite, nickel chromate, again, completely different peak shapes. The satellite structure looks different. The main peak structure looks different. Then a true chromium or nickel 3 species has different structure and shape and position again. And so what you end up with is these large tables that define a bunch of peaks. It defines their area ratios, their splitting, their full width half max for given pass energies of your instrument. And if you plug these systems into a peak fitting software, you can then mimic the peak shapes that you're seeing. And the way we do that, reason we do this, instead of just saying, in say something like infrared spectroscopy, you can actually do spectral subtractions of whole spectra, right? And that works usually pretty well. But with XPS, there's some issues with things like the charge correction is only good to, say, for the adventitious carbon has a plus or minus of 0.1, 0.2 EV attached to it. If I take a spectrum on my state-of-the-art Kratos Axis Supra, and then someone gives me a spectrum from, say, an older instrument that has a poor resolution, the spectral subtractions won't work anymore because you've got these wings on the end. So we do it this way so that I can apply it to a variety of different resolutions, different instruments, etc. And it's more universal.
5 minutes.
And I won't get into the backgrounds, but then you can see that we've plugged these fitting parameters in and we're able to quantify the different species that we have. And again, for a variety of different systems, we've been using these for many, many years and it works really quite well. What you need to visualize is what we're really doing is we're fitting whole spectra. We're using all these peak fitting parameters to fit whole spectra based on standard samples under our spectrum here. So we have the kind of the line shape for nickel oxide, nickel hydroxide, nickel metal. But it's the kind of that background work within the software that allows us to do this effectively. Whereas if you tried to do spectral subtractions, it would work great if everything was taken at the same settings on the same instrument, same charge correction, it's fine. But then you try to apply that to someone else's instrument, it's not universally applicable. And so once we've quantified, say, okay, we have so much, nickel oxide, nickel hydroxide on a nickel metal surface, we can then say, okay, well, how thick is that oxide? And so there's equations out there where, based on work from Carlson and Strohmeyer, where they factor in things like the inelastic mean free path, and you can figure out how thick your oxide layer is. But that's usually based on a single oxide species on top of the metal. So then when we've taken the information that we've gotten from these sorts of fitting procedures, and we can then use a weighted average to figure out, okay, I can now plug in the inelastic mean free path for nickel oxide as well as the inelastic mean free path for nickel hydroxide, which are very different. Figure out the weighted average of how much each I have from my fitting procedures, and then get a little better quantification of the oxide thickness of these surfaces. And we've made calculators where you can just kind of plug in that information in and pop out how thick your oxide is. It does have some assumptions. So for example, here, this one here, it measures out to about a 6.2 nanometer oxide and hydroxide film thickness. So these types of calculations, they kind of assume a homogeneous oxide layer, which is certainly not always the case, but it is a quick way to compare a series of samples. So similar work we've done for things like manganese, cobalt, iron. With manganese, you have manganese 2, 3, 4, 6, 7 oxides, oxyhydroxides, hydroxides, so you get more complications. Things like cobalt, again, a wide variety of species that are possible, and you've got to take that all into account. Iron is the worst, in my opinion. A lot of times you'll see in the literature that people say, okay, they try to fit iron 2p spectra to say, okay, I've got so much iron 2 and so much iron 3. I don't buy most of it. A couple of things that go on. First, you have a variety of systems. They each have unique multiplet structure and shake-up satellites. They all have overlapping binding energies. The metallic 2p3 halves satellite structure overlaps with the 2p1 halves metallic peak. As you increase the complexity from, say, the metal plus one or two oxides, as you add oxides, it gets a lot more difficult to quantify or even identify the species. If you have 2 species, it's generally pretty good. 3 or more species, moderate. 4 or more, you're not likely to be able to say much beyond saying you have, well, I have some oxide 2 or 3 present. If you can get complementary analysis from Raman or other things, grazing angle XRD, that can be very useful. That said, we still can do some fitting. For example, over here, we will quantify, how much metal versus how much iron, Fe2O3 versus Fe3O4. And you can see all these peaks kind of overlap, and they're all in the same area. But there's enough change in the spectral shape to be able to fairly accurately quantify what we have with 2 species. 3 species, it starts getting a little more dicey. But in a series of samples, yeah, we can see that we've got some changes going on. In this first sample, we have so much FeOH, so much FeO, so much Fe2O3, and that's changed. The amounts have changed somewhat as we've gone to our second sample. And it's believable and fairly consistent. So after you do all that kind of stuff, you can then start pushing the limits a little more. If you take a combination of data from the survey scans, so your quantitative data, as well as information from your high resolution scans, so your chemical state data, You can then factor out things such as your adventitious carbon overlayer. We have some calculators that allow us to do that. You can then use simple math and data from both those systems, so the survey scans and the high resolution results, to get a more complete picture of what you have at the surface. So for example, this was a nickel chromium molybdenum alloy surface that had been doing a variety of different electrochemical treatments. And for each of these surfaces, we were able to go in, figure out what all the chemistries were, and then match that up to the amounts that are present in the survey scan, and then be able to say, okay, so on a surface, we have we're seeing so much metal, so much of the variety of different oxides present. And then we could see those change as we go through various systems. And so it's a nice visual way of looking at it. Say, okay, here I started with some nickel hydroxide, but we have way more nickel hydroxide here. This one has a lot of chromium hydroxide. This is way more chromium hydroxide in these systems down here. So why is that going on? There are some depth and layering effects that are accounted for. For example, we've shown by Toff, Sims, as well as grazing angle work, that these things layer up. So you have your nice metals down below, that's your bulk alloy. Next to the metal are your more your oxides. So we have our nickel oxide and chrome oxides are right up against that surface. But then the outer layers, which have been exposed to air and water and whatever else is going on, those are where your hydroxides are. So there's some layering to these structures as well. And you can figure that out from things like Toff Sims or angle resolved work. We've done some Auger depth profiling, etc. All right, one more section, the Auger parameter and Wagner plots. So these are some other tools in the XPS toolbox that allow you to figure things out. The Auger process is a three-step process. You get a photo emission of an electron, and then you get a transition of an electron from an outer level down to the where the photo electron left, and then you get the kicking out of another electron. And so that's the Auger process. If you, in Spectre, you'll note we have our core electrons, but we also see Auger peaks in the X-ray photoelectron spectrum. So if you take it's the addition of the kinetic energy of the Auger electron transition and the binding energy of the core electron transition, you get what's called the modified Auger parameter. And I won't go through the math here because they'll all fall asleep, because I know I will. If you look at something like, say, the cadmium 3D 5/2 peak, you can see all these binding energies here, and they're all very similar for a lot of different species. In fact, we have a total range separation of only 1.7 EV, and that covers everything from the cadmium 0 to a variety of cadmium 4 and 2, or cadmium 2 and cadmium, these are more into other species. But there's not a lot of separation there. So if you got a binding energy peak, you'd be kind of, they kind of all overlap, and so it'd be very difficult to figure out what species you have. However, if you look at the Auger parameter for these species, you can now see that we have a total range of separation of 4.4 EV. So things are much more spaced out. And so it clearly separates out the different species. So particularly, for example, say cadmium oxide versus cadmium hydroxide. And so that's very useful to us to be able to do that. The Auger peaks also have information within them. So for example, if you look at copper, and if you look at a series of copper 1 or copper metal species, the 2p3/2 peak is basically a single sharp peak at almost the exact same binding energy. So it's very difficult to tell whether you have copper 0 or copper 1 from just this peak. If you do if you take the Auger parameter, you can then say, okay, well, yeah, things shift around. And if it's a pure system, you can then tell very easily. But if you have a mixed system, you can see that things are changing within this Auger spectrum. The shape of it's changing, the position of it's changing, even though this peak is still the same. And so this one is mostly copper 1. This one is mostly copper 0 with a small amount of copper 1. And then this one in between is kind of a mix of the two species. So we're getting information from the Auger parameter, and we're also getting information from the shape and position of the Auger peak. And so we've gone a step further where we've taken a whole bunch of standard samples, and we've now developed curve fitting parameters for the Auger peak for the copper, because it has all this rich shape information, shape and position information that the 2P system does not have. And so it's allowing us to do curve fitting of the Auger peak and figure out, okay, how much copper metal do I have versus copper 1 oxide versus copper 2 hydroxide, etc., and quantify those things. Some of the reasons we're looking at copper so much right now is we've been working with the Nuclear Waste Management Organization over the last, got to be 15, 20 years now. They're looking to bury spent nuclear fuel underground for the next, hopefully, 1 million years without it leaking out. And so they're building these containers that are steel containers that are clad in copper. And copper can stick around in the environment in its native form for a long, long time. And so we're doing a lot of electrochemistry and surface analysis and et cetera on copper. And so that's why we're looking at copper. And so we've done a bunch of work where we looked at different copper species. And again, if we look at, say, copper 2 species, you can see that that shake-up structure can be very diagnostic of different species that are present. So like copper 2 chloride has a very nice shake-up structure that's very different from, say a copper phosphate or a copper sulfate. So that's diagnostic, as well as, again, the shapes of the Auger, shapes and positions of the copper Auger peak is also diagnostic. And so it's not just binding energies we're looking at anymore. The shapes of these peaks are telling us information. And again, we could tabulate all these different binding energies and modified Auger parameters. We've developed calculations where we can look at the size of the shake-up structure and figure out, okay, how much copper 2 do I have versus copper 1 and copper 0? And then finally, we've done curve fitting of the Auger structure, which has allowed us to be able to quantify how much of those species are present in that. And so we're always looking for new ways to try and solve these sorts of problems. And each element is a little bit different, but we've got a lot of different tools in our toolbox to allow us to understand what species we have present and then quantify the species that we have present. And so this work has gone on, like I say, started back in about 2003, 2004 with myself and Andrew Grosvenor, who's now at the University of Saskatchewan. And then over the years, we've worked through a variety of different, all the different transition metals, particularly the first row transition metals, figuring out ways to quantify, to qualify and speciate all the different things that are present. And finally, a plug for my website. This is X-ray photoelectron spectroscopy reference pages. It's just kind of a repository of binding energy references, tables of Auger parameters, binding energies, how to go about curve fitting things, strange things that you'll see, etc. Kind of have a list of all the different elements down the side here. And that's my presentation. So I'd be happy to take any questions from you.
Thank you, Professor. It was an interesting presentation. I learned a lot.
Good.
We are using XPS for several analysis, but for sure it's more like simple analysis from biomaterials, but sometimes you have difficulties to understand the multiplets, or which multiplets do we need to apply, or how can we perform one specific analysis. Before to open the questions, I just want to say that Professor Marc-André Fortin, he had to leave because he has some, I think he has a class right now. So he thank you for your presentation, and sorry to left.
No worries, no worries. The times we live in right now, right? There's always the next Zoom meeting to get to.
Exactly. So it's open for questions. If anyone will start, I will start with one from Professor Marc-André. He asked you, rare earths are often a nightmare to analyze due to multiple unpaired electrons. Are there guidelines for constraining the width of electron bands in the complex rare earth peaks?
The rare earths, yeah, there's a whole nother level of complexity, and the big problem with the rare earths is there hasn't been a lot of work done on them. We were looking at, I've done a bit of work in europium, and you know, I've seen some stuff, but there's just not, other than a few reported spectra, like, and in some of them they don't even have reported spectra. For some of them really oddballs, but yeah, they have complex peak spectra, and you really have to look at if you're looking at a system, you want to be able to, you're going to have to run some reference spectra to start with, I think, if you're looking at rare earths. So if you're, you know, look at some of the oxides, and then, but getting them is even, it's difficult to even get standards for some of these. So we had that trouble with europium, where we were trying to figure out, I think it was europium 2 or europium 3, and it has odd structure, and I know the lanthanum and cerium, and they all have this big peak shapes, and you have to go through and do like what I've done with nickel and chromium, and make peak fitting parameters. I probably have some of them done somewhere saved in my files, but it's the same sort of system where you've got to run standard spectra on the instrument that you're in, at the same sort of settings. We've done that with uranium, whereas we have some students that we're working on uranium chemistry, and they've developed their own processes and procedures based on standard spectra to quantify how much uranium 4, uranium 5, uranium 6 that they have. But it's basically the same sort of thing that what we've done with the first row transition metals.
Okay, thank you a lot. Here in the chat, people are saying, thank you, Professor Marc Biesinger. Thanks for your presentation, I've learned a lot. Other questions?
I have a question, Letty. Thank you very much for your presentation. I was wondering, for example, for chromium, you mentioned that we can really detect if it is chromium 3 or chromium 6.
Yep.
To start, should we use the same FWHM for both the oxidation levels? Or?
The chromium 6, based on standard spectra, has a full width half max. We generally let it float between 1 and 1.5 EV. Mm-hmm. The chromium hydroxide is a kind of a thick thing. The chromium 3 hydroxide is more, it's like a 2.5 EV wide peak that we use to mimic. It's wide because it's multiplet split, but it's not a well-resolved multiplet splitting. Mm-hmm. With chromium 6, there is an overlap with chromium 3 part of the multiplet structure. Okay. And so it can be, it kind of limits your detection limits a little bit. So you kind of need at least, I like to say, around 10% chromium 6 out of your entire amount of chromium before you can start really saying, okay, for sure I have chromium 6 there.
Okay.
You have to be careful that you're not just falsely sticking in a small peak and saying it's chromium-6 when really it's just kind of some noise within a chromium-3 spectrum.
Mm-hmm.
So, because it's one of those things, right, where you start saying you've got chromium-6 within something, people are going to start saying, well, that's dangerous, and they're going to get very worried about it. So you want to make sure that you're really seeing the peak. So that's why I kind of put a detection limit of, you know, like I say, 8 to 10, 5 to 10, 10 to, depending on the instrument, right? And depending on the system, how strong your spectrum is. There's some detection limits that you've got to kind of factor in there before you really start saying, okay, yeah, I've got chromium-6. We're doing some work on that right now in, it's actually in the cosmetics industry. There's cosmetic, the tanning industry, sorry, it's a different, cosmetics is nickel. Tanning industry is chromium. And so whether you get a piece of leather and it's been tanned with chromium products, and so, you know, is there chromium-6 remaining on that, or is it okay that it's just chromium-3 remaining? And so we try and quantify how much chromium is present.
Thank you very much, because also it's important for biomaterial to detect chromium-6. Yeah,
we're doing some work in that area where we're trying to figure that out.
Thank you very much.
You're welcome.
So, okay, Jacopo?
Yeah, thank you. Thank you very much. Thank you, Mark, for the presentation. It was really nice. Honestly, I learned a lot. I have one question. I know that it's outside the topic, but I have two questions. Can you comment on the preparation of the sample, problem of pollution first, and after, what do you think about just few tips that you can give us to have a very good analysis in depth when you have etching? What do you think about? What's your experience on that?
Okay, so sample preparation. There is a lot of things that can go on. I do a lot of samples where if you get samples that are kind of semiconductive or insulating or partially insulating, you can get a problem called differential charging. So I do a lot of my samples, I actually electrically float. So I'll put them on a glass slide or on 3M double-sided tape. And so they don't have electrical contact with the holder. And that can eliminate a lot of problems where you have with what they call differential charging. I'll refer you to my website for more detail on that kind of phenomenon. For something like powders, I mount a thick, I put them on a 3M double-sided tape, just a layer. You want to make sure you got a thick enough layer that you're not seeing the tape underneath when you're doing your analysis. So you have to watch those sorts of things. Yeah, it depends on your samples. You know, some samples are really delicate and they don't last under either the X-ray beam, they'll degrade, or the action of the charge neutralizer will cause them to degrade. You get thermal effects. So something like a copper 2 hydroxide, you put it under an X-ray beam and it reduces under the X-ray beam very quickly to copper 1. Just from it's like a thermal effect because the X-rays heat that material up. So you can do things where you cool the sample with liquid nitrogen attachments that allow you to cool a stage in the sample, so it allows you to analyze the sample. Polymers can do the same thing. I've seen polymers, most of them are pretty good, but I've seen some delicate stuff where you can almost see it melting and burning within the instrument, you know, discoloring as you're hitting it with X-rays. So degradation of the materials under the X-ray beam can be an issue. For etching or depth profiling, the new gas cluster ion sources are quite a revelation. They really do allow you to do depth profiling while maintaining the chemistry of your material as you go into the material. And I've seen it work for oxides. I've seen it work nicely for polymers. It really is a revolution, these new gas cluster ion sources compared to the old monatomic source, which were great. You could depth profile, but I would never trust chemistry after something's been sputtered with a monatomic argon ion source. For most part, you would get reduction of materials. You get a lot of mixing and damage. And so I would just look at quantifying. I wouldn't look too much at the chemistry. I just didn't trust it very much. But with the new gas cluster source, it's quite good. Does that kind of answer your question?
Yeah, it's pretty good. Yeah, it was pretty good. Thank you very much, Mark.
Okay.
Any other questions? May I have a stupid question, Professor?
Sure. There are no stupid questions.
No, I don't know. But actually, is the shake-up the same word that you can use for satellites or no?
They do kind of use them interchangeably. There's some physics in behind there that I've seen shake-up, shake-down, and then I've seen them called satellites. I don't worry. I just call it structure, and I let the physicists, they'll go in and they'll do modeling, and they'll say, well, this is the D9 to D10 transition, and I'm an applied chemist. I don't get into that stuff.
Okay, I get it. So,
but
okay,
yeah, the physicists will go through and they'll look at all that kind of stuff, and they'll do the math and computer simulations to try and figure out, what kind of transitions they are, and what's the physics behind it, which is interesting and important. Mm-hmm. But from my point of view, I use it as I'm grateful that that stuff is there, because it's diagnostic for chemistry.
Sure. Sure. And I have a final question. I'm so sorry. And sometimes I read in several papers that sometimes they don't do multiplets, for example, for transition metals like iron or I don't know, manganese. Normally they do like a huge area containing like 3 or 3 multiplets. Is that correct? We can do that, or what kind of information you can lose?
So if you have so for, say, iron, if you have iron oxide or iron, Fe2O3, Fe3O4, there's multiplets there. If you have low spin iron 2, so pyrite, mm-hmm. or ferrocene, right? Mm-hmm. You have, for low spin iron, there's actually no, the electrons that are there are actually paired, and you get a single sharp peak. Okay. Right. So if mm-hmm. if you're analyzing something like a ferrocene or an iron would have some organics attached to it, it may give you a nice single peak without multiplets.
Okay.
But otherwise, in most of your oxides, your sulfates, your iron silicates, your iron aluminates, your iron, most of those are unpaired, and you'll get varying shake-up, or your varying multiplet splitting structures, and sometimes varying shake-up satellites within the iron peak that are very different. So when people say they try to quantify and say, well, I've got iron 2 and iron 3, I don't believe it very much unless they are proving it based on spectra, because I've just shown the oxides and hydroxides, right? But mm-hmm. there are carbonates, there are mixed metal oxides, mixed sulfates, all those other things. They'll all have different structure within the iron. Just like nickel was really, you could see it in the nickel, because it was really different. All those different things had different peak shapes to them. And so when people just they take systems and they say, okay, you've got a mix of oxides, metals, sulfates, and then they just say, well, I've got iron 2 and iron 3 here. I don't believe it, because that could be just iron 2 with more satellite structure from a specific species versus, so yeah, they try to simplify it when it's not simple.
Okay, I see. I see, because I saw sometimes they are just mixing everything, and I just question myself, well, how can we do that? But honestly, so it's not so accurate.
And you have to look at the whole system, right? And I see this issue a lot in when people go and curve fit the oxygen peak. And they get focused on, well, I'm interested in chromium oxide and chromium hydroxide. So you have a nice spectrum of, you're taking your chromium 2P and you're taking your oxygen 1S, and you say, okay, well, I see chromium hydroxide and chromium oxide. Therefore, all my oxygen peak is just chromium oxide and chromium hydroxide. But they don't take into account that there's an overlay of carbon with oxygen associated with it. They don't take into account that, oh, I've also got some silicon oxide mixed into that material. I've got some other species, I've got some sulfate, I've got some this and that. And they don't realize that all those oxygen species are also in that oxygen 1S spectrum. They get focused on just the one element, and they don't take into account the fact that there's a whole bunch of other things going on in there. And so people get into trouble, they try and curve fit the oxygen peak with the only thing that they're interested in, and they just forget about all the other stuff that's there that's contributing to that spectrum.
No, that's true. Oh, thank you a lot. So if you don't have any other questions, I would like to thank you again, Professor Biesinger. It was a pleasure to hear you today.